We're live. So chapter 13, correlation and linear regression. We'll be looking at how to explain the purpose of correlation analysis, calculating the correlation coefficient, applying regression analysis to estimate the linear relationship between two variables. We will be evaluating a regression equation's ability to predict the standard estimate of error of the coefficient of determination. And when you hear the term correlation, what comes to mind?
How they're related.
How they are related. Okay. Something that looks like this. Actually, let's keep it a little bit smaller right now. We're going to have two variables. First off, what kind of graph is this?
Scatter.
It's a scatter. All right, so using the scatter, we are able to compare the relationship between two variables. Hey, right now, would you say that there is a correlation between these two variables?
Yes.
Is there correlation? Correlation in this variable. Correlation.
I don't think so.
All right, I would define this as positive correlation, negative correlation, and no correlation. Here we can observe a relationship in this direction. Here we can observe a relationship in this direction. Here, not so obvious. So the correlation coefficient, we are going to say, and reference this with a lowercase r. So the correlation coefficient, who can define it?
The measure of the strength of the linear relationships between two variables.
Measures the linear strength in the relationship between two variables. We identify it with a lowercase r. It shows the direction and strength between interval and ratio level variables. It ranges between 1 and -1. So we're going to know that it ranges from 1 to -1. A correlation of 1. We're going to say that this is perfectly positively correlated, or we would say that there is the strongest positive correlation. What do you think we say at -1? We say that there is an inverse or a strong negative correlation. So the strongest correlation, because it's up to its parameter. What's in the middle here? 0. So what do we think we say if we identify a correlation coefficient of 0?
Would that be no correlation?
No correlation. All right. Flip over to page 433. I want somebody to give me, what is the formula for solving for correlation coefficient? I'll start you out. It's the sum.
R equals the sum of X minus
The sample mean
times Y minus
what to help him. What is Y bar? Where is our cheat sheet in the text? In this example, in this formula, what is Y bar? Go ahead.
Is it the sample mean for the Y variable?
Absolutely. The sample mean from the Y variable. Good job. Remember what we said. Correlation coefficients analyzes the strength of the relationship between two variables. Here are our two variables. Okay, let's go through an example. I want you to bookmark page 433, table 13.3. On page 433, table 13.3, where you see deviations from the mean of their products. We're going to rely on this data to go through this problem. All right, so sales manager. All right, so the sales manager of Copier Sales of America, and I'm going through the problem on page 443. So the sales manager of Copier Sales of America has a large sales force throughout the United States and Canada. Wants to determine whether there is a relationship between the number of sales calls made and the number of copiers sold. So the number of sales calls made in a month and the number of copiers sold that month. The manager selects a random sample of 15 representatives and determines the number of sales calls each representative made and the number of copiers sold. This data you'll find on page 444. So we start out with Brian. Brian made 96 phone calls and sold 41 copiers. Okay, let's go back and define. In this formula, there's X and X bar. So here is variable X and the sample mean from variable X. Is this my dependent or independent variable?
Independent.
So X is independent. I don't have to write that. You'll remember that. Okay, first, standard. All right, so the first step, we're just going to flip back here. All right, what's it tell us to do first? The first step in determining the regression equation is to what? Find the slope of the number. All right, we're taking you back probably to an earlier time in life. But who before has calculated the slope of a number?
In 1 year, Charles.
What's our formula?
B equals R, and then it'd be standard deviation of Y and standard deviation
Of X. Okay, let's go back and see from our chart on page 433. Now, the text has done a good job of summarizing this for you. So remember, it's the standard deviation of the Y variable and the standard deviation of the X variable. But the book has given us a good job of being able to solve this. Okay, so flipping back to I got ahead of myself. Go back to page 429. First, we're going to have to solve this. All right. Now, we're going to look at the data on page 428. And we're still looking at the relationship between sales calls made and the number of copiers sold. Manager last month, looks like Ron made 180 sales calls, and how many copiers did he sell?
70.
70. And everyone sees this data on the top of page 428. Okay, now in this example, number of sales calls. Is this the independent or dependent variable?
Independent.
Number of sales calls is the independent variable. The number of copiers sold is the dependent. Now, another thing that is customary is that we will put the independent variable on the x-axis. So if you look down at the chart, you'll see sales calls is on the x-axis. Copiers sold on the y-axis. All right, so using this data, how are we going to solve for the correlation coefficient? We're going to have to find the means of x and y. Excuse me?
Is it somewhere written down here? I'm just missing the answers for the means or
I would say if it's not jumping out, let's start. But I'm going to say, let's look at the top of page 433. Go back to that example. Look at this top formula. Do you see that data given in this example? What is that number? Look on the far right column. The sum, 6,672. Now, if that's not given to you, how are you going to solve for that? You would have to build that chart on table 13. So first, you have your sales representatives. You have the sales calls. And you have how many copiers each representative sold. And you'd have to build that out. Now, what's the standard deviation? Well, first, how many variables do we have? How many sales reps do we have? We have a total of 15. Nora, can you see the blue?
Yeah.
Okay, I won't go any further to the right. I'll keep it here.
You can go further to the right. Like, we can still see half that piece of paper that's hanging on the board.
Oh, sweet.
It's really angled there, though, Charlie. I'll angle that much.
Yeah, I see now. Right now, my camera is angled a little bit more to the right. Okay. So you're right. I probably can't go much further out this way. All right, so what's the standard deviation of the x variable?
Um, 42.76.
42.76. What's the standard deviation of the y variable? Solve that equation.
I got 0.8646.
0.75.
Yeah, right.
You said
I
0.8646,
got 0.8646.
and I just rounded you up to 3.
Something different, you know.
It's 0.865. Yes. Now, someone interpret this for me.
Is it positive?
Positive correlation. What would have happened if you would answer would have came out 1.2?
It's positive, but it's not strong.
It can't, I guess it can't.
It can't. You know, you miscalculated out here. Remember, the range is between -1 and 1.
Just -1 and you say 0.2.
I said 0.12.
0.1, no.
Okay, so with correlation coefficient calculated at 0.865, we know we're within our range, and we would interpret this as strong positive correlation. And remember, because we have that positive parameter, it gives it more meaning. We know how close in relationship we are.
Can you give a positive, so that means the line or the correlation of the line will be going from negative to positive, right?
Correct. So what we're seeing here is that they're positively correlated. So the more calls, what this would, I interpret this further, the more calls an individual is making, the more copiers they're selling. This is what the data would suggest to this point. And if we look at the chart on page, you know, all the way over on 441, you know, I'm getting ahead here, but you can see it visualized in chart 13.7. You see there from that chart, positive correlation. Okay, now we're back to slope. So here, we just calculated the correlation coefficient. Now we're going to calculate the slope of a regression line and a Y-intercept. Okay, so here's the slope. Let's solve for this. We just solved for
0.865. And then it would be standard deviation of Y. Saying 12.89. And the standard deviation over the standard deviation. No, that's right. Yeah, and then over the 42.76.
Oh, line. Yeah.
Okay, now
About 42.76, 42.76.
46.
0.2607 or 0.261.
Point what?
0.2607. I don't know how many decimal spots you want to go out.
We just keep it at 3. What do we have?
Yeah.
So 1.
1.
Yeah.
What do we do next? Next, we got to calculate the Y-intercept. How are we going to solve for the Y-intercept?
A equals mean of Y minus
All right, so let's solve for this.
it'll be 45 minus
The mean of Y, 46 minus.
E was
Minus,
The slope.
0.865.
Bless you.
0.265.
times, and that mean is 96.
So equal 19.
$18.944. So, what becomes the regression equation? Let's interpret it. Tina, you still seeing this?
Yep.
Okay. Fill in the rest. There's your regression equation. So if a salesperson makes 100 calls, she can expect to sell 46.04 copies. How are we going to find that? By plugging 100 in here at the end.
Can you repeat that, Charlie?
This tells us on page 443, a A salesperson makes 100 a call. Let's plug in 100 right here. Find this as 100. And solve for that equation. $46.044. This allows us to estimate. Think of this as a tool for data analysis, for planning. That someone knows if they make 100 phone calls, they will expect to sell 46.044 copiers. You would know if we substituted 200 phone calls, how many they would sell.
96.088.
96.088, but you could put in any variable here, which takes us back to this linear relationship. I've not used red. What's it mean to have a linear relationship? When you hear a linear relationship, a straight line. Okay, when you hear the word a straight line, this is our linear relationship. The book's going to introduce you to something that it calls the least squares principle. And let's just say that we have this type of data. Okay, the least squares principle is going to show us how to draw our graph in a way that will pass through this scattered diagram to the point to where it is minimizing the distance from each data point to this regression line. We call these items out here outliers. And I'll say when you're doing data analysis, always it's important that when you find outliers, you don't automatically dismiss them as insignificant. You know, you still want to investigate why are they outliers out here. Especially if you see more than one or you start to see a pattern of them coming out here. Okay, back to this example though. How can we draw the regression line for our copier data? Using this here.
Y-intercept would be 19.944.
So the Y-intercept is 19.44. Where am I going to start? Which one's the Y-axis? Y to the skies. So let's just say that We'll call this up here at the top 25 and call this 0. And we were at 19.944. And let's look at a particular individual. Let's look at Jeff. How many calls did Jeff make? So let's define this. X as 164. $62.748. So we have the Y-intercept here. What's next? And I think 200 would take us out. Yeah. Top sales calls, we're at 180, so we're going to say our x-axis runs from 0 out to 200.
So
All right. We're going to come out here on the x-axis. How many calls did Jeff make? So we're going to assume this data point is here. And then we go up to 62 point. We would have to say that this goes higher. Let's take this out to 100. And we go vertical to 62.648. Let's just say that data point is there. That becomes the regression line. Now, because it runs in a straight line, because of this linear relationship, you see how this can be used in planning. Because once Jeff, we'll give Jeff credit down here. Jeff knows that at any point, what might he expect? If he extends, because we have positive correlation, we would expect that as sales calls increase, the number of copiers sold. Here, he's able to estimate, he's able to plan how many more calls he'll sell, or excuse me, how many more copiers he'll sell at various stages of sales calls made. We good? All right, let's look at an example of correlation analysis, specifically with hypothesis testing. Go back to our copier example. Okay, so now we want to determine whether there's a relationship, and we just did this earlier, but a relationship between the number of sales calls made and the number of copiers made per month. How could I apply this to hypothesis testing? So remember our five-step process.
So, number of calls.
Nora, can you see the board?
Yes.
Okay. What's the first step? Okay, we have to come up with a hypothesis. When it comes to correlation analysis and hypothesis testing, what's going to be our hypothesis? Okay, so first, we're going to state our null hypothesis. And the null hypothesis is that the population is equal to 0. So stated differently, the correlation in the population what's our alternate hypothesis? And how would I interpret that?
Correlation in the population is not equal to 0.
So we're going to say correlation not in the population. So the correlation in the population is 0. And then the correlation in the population is not 0. What's step 2?
So, is that PM there the same thing on page 448 as like B? There's somewhere in our picture.
Level of significance.
All right, level of significance. And what's going to be my level of significance? What would you use?
Set 99.
I think 0.01.
5, not 0.
All right, I see 5. I hear 1. If it's not given to you,
No, 5.
He told us this was somewhere.
I told you this somewhere. I like that answer.
0.05.
And why are you using 0.05?
Because it's like consumer research.
Most widely used test statistic in consumer research. Remember, 0.05, consumer research. 0.10, political polling. 0.01, quality assurance.
It's just like checking that the stuff is good, but so manufacturer.
All right, so we're going to use 0.05. What's number 3?
Decision rule?
The decision.
What does that identify test statistic?
What's going to be my decision rule? Flip over to page.
No, it's hard to test. Just
Is there a question?
No, I think they skipped, they didn't determine our test statistic before the,
What we're doing right now.
okay.
All right, so let's look at page. Where's our formula? Flip over to page 437. And specifically look at formula 13.2. What test are they going to run?
T-test.
A t-test. Now, I will tell you that when you are running correlation analysis in this example, you're going to use the t-test. And how many degrees of freedom does it tell you to use?
N-2.
N-2 degrees of freedom. Now, what's this formula for the t?
Equal the square root of, oh wait, R will be power.
My blue ink's got a little bit better. So the t is equal to what?
Correlation coefficient.
Correlation coefficient times
Square root of the sample size minus 2.
what are we dividing this by?
Square root of 1 minus the correlation coefficient squared.
And we said with N-2 degrees of freedom. All right, now, what's this? Formulated decision rule. So how are we going to formulate this decision rule?
Are we gonna calculate that right there?
Well, first we got to hit, we're going to calculate this. First we got to set our decision rule, then we'll calculate.
The heck? Firework. Is that the speaker there? Oh, it's internet.
That was a, it did sound like a
Fireworks.
firework to start out with. Okay. So how are we going to put up this decision rule? First off, is this a one-tail or two-tail test?
Two-tail.
Okay, so it's going to be a two-tail test. And we're going to have something out here as our critical values. What area is going to be out here?
Region of rejection.
So it's just a region of rejection.
It's negative, right?
We're at a
Negative correlation.
0.05% is our level of significance.
Five.
Yeah, right.
0.005.
All right, and remember, if we're in this area, we're not going to reject. Okay, so let's go back now. What's going to be our decision rule?
That we're using.
Let's flip back to our t-distribution in the back of the book. And in this prior example, what was our sample size?
15
15. How many degrees of freedom are we using?
minus 2.
15. We're with 2 degrees of freedom. So let's go to 13. Come over to the 5%. Where am I? 2.160. So our rule is going to be, we are going to reject the null hypothesis if what?
If T
What was that, 2.160?
2.160.
Or if T is less than 2.160. Remember, either side.
So if it equals 2.167, we're accepting. We're going to have to equal that to accept it, right? Oh, no, it can be anywhere in the middle.
Anywhere in the middle. If we're here, we're going to accept it, we're going to reject it. All right, step 5, what is it?
Make a decision regarding.
Well, take a sample, calculate.
Shouldn't it be T is less than negative 2.167?
We can put it there.
That's why I was thinking I was confused. Yeah.
All right, so let's first, anyone remember the correlation coefficient?
0.865.
What was it?
0.865.
0.865.
T equals 0.865.
All right, so if we solve for this right here, 0.865.
How's the square root of
What was our sample size?
16 minus 2, which was 13? And then that is all divided by the square root of 1 minus 0.865 squared.
And it's important to note that we have previously calculated the correlation coefficient to be 0.865.
I got 6.215.
I got 6.216. So let's interpret that. Our test statistic, 6.216, is it greater than 2.16? So we are going to what?
Reject.
We are going to reject the null hypothesis that the correlation coefficient is equal to 0. Which is this up here.
You said by 9.
I said by 9. 1 minute. Any questions?
Okay, Charlie, so I have a quick question.
Shoot.
Hypothesis. So the correlation coefficient, you know, we're going into it knowing that it's 0.865. So that's obviously closer to 1 than it is to 0. But this, by doing this, we're just confirming what you can infer initially, but this is, does it make sense what I'm asking?
Yes, I mean, before we calculated that the correlation coefficient was 0.865, we identified that that was positive. And you're right, closer to 1. Now, what we were initially hypothesizing was that the correlation was 0. And you're right, we rejected, which would again, at this level of significance, we support that this is not 0. Good question. Did that answer your question?
Yes, I think so.
Well,
So is that always going to be the assumption that it equals 0 or it don't equal 0?
this will only be your first assumption.
So can you turn that result to the cells and compute what would be any testing?
Yes, we would say that there is correlation.
So it is significant. So at a
We're
significant
rejecting that there is no correlation.
research.
We're rejecting our null hypothesis. And our null hypothesis is that the correlation in the population is 0.
If it's beyond public.
Okay, and we're rejecting that. And again, when we calculate it here, we know that there's correlation.
Like why?
We measured here even the strength of that correlation.
cheesy. 6.216. And then you put that over the T, and that's greater than 2.16.
Yeah, so this right here would be the 2.16, and this would be the minus 2.16. So 6.26 in that direction. It is greater than 2.16.
What is the big picture here? Because like we already knew that there was correlation, so why would we use the fact that we know there's correlation to prove that it's not no correlation? We already knew that, right?
If you first put out the hypothesis, you're right, this is going to give you, this is hypothesis testing, which again, educated guesses. What you did here is you calculated the strength of that correlation. Here you're applying it into a research method at a certain level of significance. And I would say if you came up with this answer, this might fuel further debate where someone would come back and ask you some additional steps that we covered in the first video. I mean, here, to solve for this equation, though, you've got to calculate this coefficient.
You gotta have R as our utility.
But you're not calculating, here you're, look at it this way, here you're calculating the strength of the relationship.